So let's pick back up where we left off. Apologies for the technical difficulties. What we were saying, where did we leave off? We were saying that order matters when we are constructing propositions with quantifiers. And here we were giving an example of, here is some statement with nested quantifiers, and if we switch the order of the quantifiers, then it has a totally different meaning and is no longer true. So here I want to give a couple of heuristics for what all these orders mean, what all these orders mean. And I want to say first that the best thing to do is to think about the proposition and figure out what it's saying. So you shouldn't rely on these too much, but I hope that it'll give you some idea to start with. So here are some heuristics. So if you have two universal quantifiers, then first of all, that is actually, in this case, if there's two the same, it is the same as switching the order. And in this case, my slogan is that this always works. So no matter what x you choose, no matter what y you choose, your propositional function is always true. So it always works. If you have for all on the outside and exists on the inside, you get something like every x has a partner. So that's the kind of thing we were seeing in the first example up here. Every x has a negative, right? So every x has a partner that makes our thing true. If you have exists on the outside and for all on the inside, that means something like there's an x that always works. So there exists an x that works for every possible y. And then, of course, if you have two existential quantifiers, again, these, the order between them doesn't matter. And this means something like some pair works. So it can be made to work at all. You know, something is going to work. So there are some basic ideas for you. The next thing that I want to talk about, that again is basically similar, but slightly more complicated, is negating nested quantifiers. And it's, you know, not too much more complicated. You basically are going to use De Morgan's laws a bunch of times. So it's not too much worse, you just have to do it more than once. So for example, what does it mean to say that it is not true that for all x exists y such that p of xy? So by De Morgan, you can pull this through the first quantifier and turn it upside down, or not, okay, switch what it is. So exists x such that not exists y, p of x, y. This is by De Morgan. And then you can pull it through the second quantifier and switch that one as well. Exists x such that for all y, not p of x, y. And then, if you know what this is, maybe you can negate that more clearly as well. But this is the process, is you just carry through, carry the knot through each quantifier. So this is De Morgan again. Okay. So, well, let's give another, maybe let me give an example in words. So the negation of and in fact, let me make it an example also of even more ways that you can write things differently. So every real number has a negative. What does this mean? This is another way of saying the same thing we wrote above, that for all x exists y such that x plus y equals 0, right? We're saying every real number has another real number, which is its negative. So what is the negation of this? It will be exists x. So let me look at this. I think it's going to be more convenient to negate it from that perspective. Exists, so switch that quantifier, switch this quantifier, and then apply the negation of that, which is just to say that x plus y is different from 0. And then let's rewrite this in words. There's a real number x such that for all real numbers y, x plus y is different from 0, or maybe in even different words, some real number has no negative. So there are some nice examples of that. And now I want to finish by going over some applications just for some extra motivation. I said basically similar things after we talked about defining the quantifiers, how you'll see them used everywhere in mathematics, and there are some analogies to things in computer science. But I want to give some more applications that are a little bit closer to the kind of thing that we are doing, or the kind of thing that you might be familiar with. So I just want to express that a lot of mathematics is expressed in these terms. So for example, the rigorous definition of a limit which you may have seen before, or if not, you will see if you ever take an analysis class, or even if you take 1A, possibly. So limit as x goes to a, f of x equals L. This is defined to be for all epsilon greater than 0, there exists a delta greater than 0 such that absolute value of x minus a less than delta implies absolute value of f of x minus L is less than epsilon. So basically, building up all of this machinery with logical expressions and now quantifiers allows us to make precise definitions like this. And here's another example for the kind of thing that you'll see if you start taking courses in abstract algebra. So this may not make sense at the moment, but I just want to write it down because I think you will understand the propositions at least. What does it mean that the real numbers form a group? Under addition. So a group is some kind of mathematical object that is the subject of abstract algebra. And what is a group? I mean, I'm not going to define a group in general, but what is it, you know, the real numbers are a group, and what does this mean? It means three things. There exists, or there is an x, and I'm going to start using this shorthand, st, for such that, just to save some writing. There's an x such that for all y, x plus y equals y. Which is to say that there is a 0. Second of all, for all x, there is a y such that x plus y equals 0, where this is the thing that we found in the last line. And this is saying that we have negatives. And the last one is an associative property for all x and for all y and for all z. We have x plus y plus z equals x plus y plus z. So this is a familiar property of addition, but it's one of the things that makes a group. So this is just to say that these kinds of ways of saying mathematical propositions are going to come up throughout mathematics, and basically everything is written in these terms.